Okay guys, well, we're live. I apologize right now for the microphone quality. It is very fuzzy. It sounds like I'm recording a video in 1997, but you know what? This is what we've got, and this is what we're going to be working with for the next month until we know what's going on further. So right now, I'm going to say with this reading data from Graphs Practice, this is an individual assignment. So you really should go through and complete this on your own first, but I'm going to walk through the solutions right now in case there's anything you weren't understanding. So to start, please answer your homework questions using this package. Up first, it's asking us to create a table of values to help you graph this quadratic relation. Remember, we know it's a quadratic relation because it has a power of 2. All right, the order of the equation, or the highest exponent, is 2, so that means, therefore, it is quadratic. So we've set our table of values already from x equals -2 up to x equals 4. And to figure this out, well, I'll just sub it in. So if y is equal to 2x squared minus 4x, then here I would have 2 times -2 squared minus 4 times -2, which is going to give me, that's 4 times 2 is 8, plus 8, so 16. All right, 16 right there. And then I'm going to keep moving through this. So 2 times -1 squared minus 4 times -1. That's 2, so that's 6. And then we've got 0, so that's 0. That's nice and easy. And 2 times 1 squared is 2. Now we're still going to be -4, so that's 2 minus 4. It's going to give us -2. We can see we're decreasing, not really by even intervals so far, but we know it's not first differences, it's second differences that we're looking for. So 2 times 2 squared minus 4 times 2. Is going to give me 0. My next one will be 6 and 16. Okay, so state the intercepts. We're looking for the x-intercepts. I'm going to ask you right now, what is another word for the x-intercepts? I gave you a whole bunch. And they are, pause if you need to think for a second. They are going to be the roots, the zeros, or the solutions. But we can see the x-intercepts are where y equals 0. So I have one intercept there, and I have one intercept there. And all I'll do is I'll list the x values for that. So x equals 0 and x equals 2. I'm going to graph my table of values now and use a curve of best fit. Let's see, I need to go up to 16. I didn't graph this axis the best that I could. 4, 8, 12, 16. And I'm going from -2 over to 4. I'm just going to go up by 1, 2, 3, 4, -1, and -2. Now, if you used a different scale, your parabola is going to look different. It might look stretched out or compressed compared to mine. But you know what, guys? That's okay. As long as your numbers match and you've graphed your graph properly, then we are okay in this. 0 at 0, 1 at -2, -2 is right there, 8, and back to 0, 3 is up to 6, and 4 is up to 16. So here's my scatter plot. Look at this lovely symmetrical parabola. I'm going to sketch that up like that. And I'm going to sketch that up like that. Okay, so I've graphed my values and I've drawn a curve of best fit. Challenge accepted. Use the graph to find the vertex. Remember, that's going to be either the lowest point or the highest point, depending on whether the graph looks up or down, opens up or down. So right here I see my vertex, and the coordinate is 1 and -2. And I'm going to put that right there for you. Finally, find the midpoint of the zeros. Do you remember what I actually called that before the break? I called it the axis of, that's right, you got it, the axis of symmetry. So to find that, I'm going to write x equals s plus t over 2. We're just going to make a note. S and t are the zeros. So that gives me 0 plus 2 over 2. So the midpoint is 1. And I could sketch that on right here. This is my axis of symmetry. Okay, it's the vertical line that passes through the vertex. So what information does D help us find? Axis of symmetry. Finally, F, if the point 4 and 16 is on the parabola, what other point has a y-coordinate at 16? So 4 and 16 is on the parabola, it's right here. What other point? Well, I just move across until I find it right there, and I see that it's negative 2 and 16. And I also could have seen that from my table of values. Let's flip this over. One of the maintenance staff finds a tennis ball on the school roof and throws it to the ground below. The table gives the ball's height above the ground as it moves through the air. So here I have my x variable, which is time, and my y variable, which is height. The first thing I'm asking is this data linear, quadratic, or nonlinear? And we need to know, how would you know this? So if you think you know, pause for a second. Okay, but the question is, how would you know? We need to determine the first and second differences. Okay, and that will tell us linear if the first differences are all the same, quadratic if the second differences. So let's calculate it right here. 11.25 minus 5 is 6.25. That's 3.75. Well, already we see it's not linear. 1.25, negative 1.25, negative 3.75, and you guessed it, negative 6.25. So it's not linear. We know that. Let's determine our second differences to see if it's quadratic. So 3.75 minus 6.25 gives us negative 2.5, negative 2.5, negative 2.5, negative 2.5. Are you seeing a pattern, guys? I sure hope so. These are constant second differences. So it is a quadratic relation. Now it's asking us to estimate the coordinates of the vertex. What is the highest point? Looking at our table of values, we have to estimate that. So moving across, I see, well, it looks like right here is our highest point, 1.5 seconds and 16.25 meters. In this case, what would the axis of symmetry be? Well, it would be the x value. So x equals 1.5. In this case, it's x, which is our time. So this number is representing time of the highest height of the ball. Okay, D says, is the optimal value a maximum or a minimum, and how do we know? If we just look at the data, we can see that the ball is thrown up. Also, this maintenance worker really hoofed this to have it going an additional 11.25 meters in the air. So it's thrown up and then comes back down. That is going to be a maximum value. How do we know? We read table of values. But there's another one. The second differences are negative. So therefore, the parabola opens down. What is the optimal value and what does it represent in this situation? Well, we look up here, our optimal value is the y-coordinate of the vertex. So it's 16.25. It is the height of the ball at its peak. Create a scatter plot and draw the quadratic curve of best fit. All right, here I go. Hopefully you've already done this. If not, be making adjustments right now. I'm going up to 3 seconds. 1, 2, 3. Okay, and I'm going up to 16.5 meters. 60. All right. You see, I just made it up there going up by 2s. So I'm going to start plotting my table of values. I'm going to do it in red pen so it shows up a little bit more clearly for you guys. Okay, so here I'm going to zoom out a little bit for you right now. There's my parabola. I'm going to add on a carefully drawn curve of best fit. You guys are home all day. You know what? You should maybe be working on your parabola drawings. How about that? There's my curve. This right here is the roof of the school. That's the initial height. This is where Bill, our custodian, is throwing the ball off the roof. So use our model to predict the height of the ball at 2.75 seconds. We've got 2.5, 2.75 is right here. So I'm going to draw up and across. Now I'm going to predict that the ball will be at 9 meters at that time. And when was the ball at 16 meters? Well, by the nature of this curve, it hits 16 meters at 2 separate points. All right, here and here. So if I carry it down, and I don't have a long ruler home with me, none of us knew this was going to happen to this degree. I follow it down. And I see that's about, that's 1.25, so maybe 1.3 seconds. 1.5 and 1.65 seconds. Your numbers are going to be a little bit different. This is really an estimate on that one. All right, moving on to the next page. We're halfway done. Use the following graph of y equals negative 2x squared plus 16x minus 24 to answer the question. Whoa. Here's the graph right here for us though. So A, find the zeros of the parabola. How did I find them? I looked on the graph, guys. I said there's a 0 and there's a 0. So I'm going to say x equals 2 and x equals 6. Find the equation of the axis of symmetry. Remember that our zeros are s and t, and this is going to be in a lot more later. So x equals s plus t over 2. So x equals 2 plus 6 over 2, which gives us x equals 4. That is the equation of our axis of symmetry. Determine the optimal value. We've got two options here. One is we can refer to the graph and say, hey, there's the vertex. Draw across and try and say what that optimal value is. Now, I don't know about you guys. I'm not going to estimate to a very precise value there. What I can do, though, is if I know my x value and I also know the equation for this relation, I can take this and I can sub it in. So that would give me y equals negative 2 times 4 squared plus 16 times 4 minus 24. And when I use dead mass, I'm going to put my calculator right here. I get an answer of 8. So our optimal value is 8. The vertex has the coordinates of x and y. Well, x, y. So there are our coordinates right there. And finally, what is the relationship between the axis of symmetry and the optimal value to the vertex? They are the coordinates of the vertex. We just did that. We are so happy to have made that connection. Last one. The chain of ice cream stores sells a total of $840 of ice cream cones per day at $3.50 each. Market research shows that this trend in revenue as the price of an ice cream cone decreases. So we see as they change the price of the ice cream cone, the revenue or the amount, so revenue is the amount of cash in sales. That's how much money is coming into the store each day. And it does make sense because as the price goes down, more people are going to be buying ice cream cones. But as the price drops even further, well, now they're literally giving the ice cream cones away, so they're going to be making less money. The goal here is to find that sweet spot. What price is low enough to sell, but still high enough to make a profit? Okay, so up first, fill in the curve of best fit for the scatter plot below. We don't really see a clear vertex here. One of these points is not the preset vertex, and so we need to really just kind of estimate here. I have drawn better parabolas. Today's not that big. Estimate the vertex. So let's estimate here. I think it's about here. So if I read down, it's about, 1.9. And it's going up by 2s and about 4,200. So what does this mean? For max revenue, so for maximum cash coming into the store, the cost should be $1.90 for a cone, and the max revenue is $4,200. Use your model to predict the revenue that would be produced at a price of $2.25. That's right here. I draw my line up, and I draw across to interpolate, and that's just below $4,000. I'm going to say about $3,900. So that means that if the ice cream shop charged $2.25 per cone, their daily revenue would be $3,900. After $2, why does the revenue that's earned go down as the price goes up? Okay, so price is going up here. Well, fewer people are buying cones. We like the $1 cones. Love those McDonald's cheap sundaes and ice cream cones in the summer. I'm not going to go pay $4 in the middle of winter for ice cream. Except as I say that, it is obviously a lie. I will buy ice cream all the time. Okay, but then before $2, why is the revenue lower if they're selling the cones for less?